Catalog of North Texas Earthquakes confirms continuing effects of wastewater disposal. A comprehensive catalog of earthquake sequences in Texas's Fort Worth Basin, from 2008 to 2018, provides a closer look at how wastewater disposal from oil and gas exploration has changed the seismic landscape in the basin. In their report published in the Bulletin of the Seismological Society of America, Louis Quinones and Heather Deschen of Southern Methodist University and colleagues confirm that seismicity rates in the basin have decreased since 2014, a trend that appears to correspond with a decrease in wastewater injection. However, their analysis also notes that new faults have become active during this period, and that seismicity continues at a greater distance from injection wells over time, suggesting that far-field changes in seismic stress will be important for understanding the basin's future earthquake hazard potential. One thing we have come to appreciate is how broadly injection in the basin has modified stress within entire basin, said Deschen. The first thing researchers noted with wastewater injection into the basin was the reactivation of individual faults, she added, and what we're now starting to see is essentially the leftover energy on all sorts of little faults being released by the cumulative volume that's been put into the basin. The earthquake catalog published in BSSA reports all seismicity recorded by networks operated by SMU between 2008 and 2018. Some seismic sequences in the catalog, such as the 2008 Dallas-Fort Worth Airport earthquakes, are well known and well studied, while others such as the 2018 West Cleburne sequence are reported in the paper for the first time. Deschen said publishing the complete catalog was important in part to help people recognize that there are earthquakes throughout the basin, not just on these 3 or 4 sequences that have garnered a lot of press attention. The researchers found that overall seismicity in the Fort Worth Basin has been strongly correlated in time and space with wastewater injection activities, with most seismicity occurring within 15 kilometers of disposal wells. Wastewater disposal volume began to decrease from its peak in 2014, mostly as a result of lower oil and gas prices, and the study shows tapering off of seismicity along the faults that were near high injection wells, said Quinones. There are exceptions to this pattern, including the 2015 Irving Dallas and 2017 Lake Louisville sequences that have no wells within 15 kilometers. Induced earthquakes occur when wastewater injected back into the ground increases the pore pressure within the rocks and affects stress along faults in surrounding rock layers. In the Fort Worth Basin, these stress changes may propagate far, more than 10 kilometers, from the injection wells, the researchers suggest. Injection rates peaked in 2014, but we still don't understand how spatially extensive the modification of pore pressure is at depth, so we still don't understand how the hazard is going to reduce with time, said Deschen. There are still far fewer induced earthquakes in the Fort Worth Basin compared to regions such as Oklahoma, which also has experienced a dramatic increase in seismicity in the past decade as the result of wastewater disposal from oil and gas production. The volumes of injected wastewater are much higher in Oklahoma, and the faults there tend to be much closer together, Deschen said. By contrast, Quinones said, faults in the Fort Worth Basin are more widely spaced, and there are few instances of earthquakes jumping between faults. However, the dense population of the Dallas-Fort Worth metropolitan area makes it critical to continue monitoring the region's induced earthquake risk, comparing seismic data with more information on wastewater injection. For the moment, Deschen said, researchers only have access to monthly cumulative volume and average pressure at injection wellheads, in a report that is updated once a year. It would be best if injection data were provided in a more timely fashion in Texas, and if more detailed daily information on injection rates and volumes and some measurements of downhole pressure were provided, she said. How tides can trigger earthquakes. The tides are turning in a quest to solve an earthquake mystery. Years ago, scientists realized that earthquakes along mid-ocean ridges, those underwater mountain ranges at the edges of the tectonic plates, are linked with the tides. But nobody could figure out why there's an uptick in tremors during low tides. Everyone was sort of stumped, because according to conventional theory, those earthquakes should occur at high tides, explained Christopher Scholes, a seismologist at Columbia University's Lamont Doherty Earth Observatory. In a study published today in Nature Communications, he and his colleagues have uncovered the mechanism for this seeming paradox, and it comes down to the magma below the mid-ocean ridges. It's the magma chamber breathing, expanding and contracting due to the tides, that's making the faults move, said Scholes, who co-led the study along with Lamont Doherty graduate student Yen Jo Tan. Going against the tide. The low tide correlation is surprising because of the way the mid-ocean fault moves. Scholes described the fault as a tilted plane that separates two blocks of Earth. During movement, the upper block slides down with respect to the lower one. So, scientists expected that at high tides, when there is more water sitting on top of the fault, it would push the upper block down and cause the earthquakes. But that's not what happens. Instead, the fault slips down during low tide, when forces are actually pulling upwards, which is the opposite of what you'd expect, said Scholes. To get to the bottom the mystery, he, Tan, and Fabian Albino from the University of Bristol studied the axial volcano along the Juan de Fuca Ridge in the Pacific Ocean. Because the volcano erupts every 10 years or so, scientists have set up dense networks of ocean bottom instruments to monitor it. The team used the data from those instruments to model and explore different ways the low tides could be causing the tremors. In the end, it came down to a component that no one else had considered before: the volcano's magma chamber, a soft, pressurized pocket below the surface. The team realized that when the tide is low, there is less water sitting on top of the chamber, so it expands. As it puffs up, it strains the rocks around it, forcing the lower block to slide up the fault, and causing earthquakes in the process. Furthermore, said Scholes, the tidal earthquakes in this region are so sensitive that we can see details in the response that nobody could ever see before. When the team charted the earthquake rate versus the stress on the fault, they realized that even the tiniest stress could trigger an earthquake. The tidal data helped to calibrate this effect, but the triggering stress could be caused by anything, such as the seismic waves from another earthquake, or fracking wastewater pumped into the ground. People in the hydrofracking business want to know, is there some safe pressure you can pump and make sure you don't produce any earthquakes, said Scholes. And the answer that we find is that there isn't any. It can happen at any level of stress. Of course, a small stress over a small area isn't going to cause a devastating earthquake, and the exact amount of stress needed varies from place to place. Our point is there's no intrinsic stress that has to be exceeded to cause an earthquake, says Scholes. There isn't any rule of thumb.